Right. Continuing with the laws. I just gave you the commutative law. Either claim the law or know how to manipulate the variables. Knowing how to manipulate the variables comes with practice. When you deal with the truth tables, play with the numbers. When you play with the numbers, the laws will automatically come to your head. Believe me, you will understand the laws instead of just claiming them. And it is much better to understand them. A little bit of practice and you're good to go. Right. Where are we in Africa? De Morgan's law. This one is, I think, the best of them all. This one is the best of them all. A plus B is equal to, nope, not. This bar means not. Opposite is equal to A naught multiplied by B naught. I introduced the not gate. I introduced the not operator. What it basically means, if A is equal to 0, A naught is equal to 1. If A is equal to 1, A naught is equal to 0. You will see we only deal with two variables, ones and zeros. And this is the whole truth table for the not gate or the not operator. Right. So when I say A plus B not, it means any solution you get from A plus B, the opposite of it. Now, this is the same. What De Morgan's, this is De Morgan's, what's the spelling? Anyone to help me with the spelling? I don't have the picture anymore. Morgan, more. This is the De Morgan's theorem used with all other laws to simplify logic circuits. The whole reason why we are doing these laws is because they simplify our circuits. Instead of having, if I am to build this circuit, some of you already know how to build the circuit. If I am to build this circuit, how many do I have? I have A, I have B, I have A, I have B, I have and I have OR gate. I have OR gate. Here, I've just simplified A plus B. So here the output I get A plus B. That's an OR gate. Then I have on top of that a NOT gate. So here I get the solution A plus B NOT. How many gates did I use? 1, 2. It is the same as this is A plus B. It is the same as A NOT, B NOT. How do I build A B NOT? A B. We have a NOT gate. Now we have A NOT. We also have here a NOT gate. Practice. Now we have B naught. We have A naught, B naught. These two combine with an AND gate to give me A bar, B bar. How many gates do we have here? 1, 2, 3. Here we have 1, 2. Right. The whole purpose of these laws is to simplify the circuit. Minimize the number of logic gates we use in a circuit. So, for example, in this case, A plus B is the same as A bar, B bar. A plus B bar is the same as A bar, B bar. Two solutions. But if I count the gates 1, 2, 3, the gates 1, 2, it means probably using a circuit with 2 gates, 1 is much cheaper because I'm only using 2 gates. obviously depending on the prices of each. You never know. It's much cheaper because I'm using only 2 gates. In terms of size, it's much smaller because I'm using only 2 gates. Boolean algebra definition, simplification. It deals with simplifying circuits so that we get better performance using smaller sizes and obviously using cheaper circuits. Now, going back to De Morgan's, De Morgan says A plus B bar is the same as A bar B bar. In a circuit, if you see A bar B bar, you can replace it with A plus B bar, provided you are simplifying the circuit. It's either you go from A plus B to here, provided it is going to simplify your circuit, or you go from here to here, provided it will simplify your circuit. If you are given a circuit with A plus B bar C plus A, B plus C plus A, I can simplify this circuit maybe by putting A bar, B bar here. It can be simplified. Or I can go from this to this if it provides simplification. With examples, with practice, you see which of the two works, one way or the vice versa. Now, if you want to understand how to manipulate the variables, what is the De Morgan's theorem? Use the truth table. It's simple, use the truth table. So if I have, here I have 2 inputs, A and B. I have 2 inputs, A and B. I have 2 outputs, A plus B bar, and I have A bar, B bar. But before I get there, let me do this. Let me simplify it small. Let me start with A plus B. Then I go to A plus B bar. Then I also have A bar. I have B bar. I have A, B bar bar. 2 inputs, it means 4 possible combinations. 0, 1, 0, 0, 0, 1, 1. What is A plus B? 0, 1, 1, 1. What is A plus B bar? A plus B bar, it only means the solutions you get here, the opposite of them. So we have 1, 0, 0, 0. What is A bar? A bar, this is our A. A bar is 1, 1, 0, 0. Then B bar is, this is our B, is 0, 1, 1, 0, so it's 1, 0, 1, 0. What is A bar? Multiply by A bar. What is A bar and A bar? You can either say multiply, which is for someone who doesn't understand the logic designing, or you say A bar and B bar for someone who understands his or her operators. Either way, in the exam you will pass, but the goal is not always to pass, it's to understand what you are doing. And by understanding, you no longer use plus, but or. So this is A or B. This is A naught. This is A bar and B bar. Right, we continue. So A bar, B bar is a little help, participation. What is A bar, B bar?
It's 1, 0, 0, 0.
1, 0, 0, 0. Anyone so far having problems where these numbers are coming from? Nope. Now, going to De Morgan's theorem. De Morgan's theorem says this is equal to this. Is it equal? Yes. 1, 0, 0, 1, 0, 0. 2 circuits, 2 solutions. The solution is the same. But are the number of gates the same? That is the answer which we need to, that is the question which we need to answer as we continue with the course. You have a circuit. you have many solutions. But are those solutions offering better performance, smaller size, smaller number of logic gates, which means cheaper? Are those solutions we have offering that? That is the reason why we are doing Boolean algebra. De Morgan's theorem, it also has the second part. The first part is A plus B bar is equals to A bar B bar. The second part is A and B bar is equals to A bar plus B bar. If you do the whole process of truth tables, even of designing the gates, you understand they are the same. Two solutions for the same problem. You know how to manipulate the numbers. We can as well do the process that we just finished doing of the truth tables, and we'll still get to the same conclusion. So these are the two laws of De Morgan. Two laws of De Morgan, De Morgan's theorem. We will use these when we are simplifying our circuit. We also have what we call the redundant rule, which says A plus A bar B is equals to A plus B is the same. Instead of having this useless gate here, we can just remove it and it will be A plus B. It is the same. I repeat, practice, draw truth tables for A plus A bar B, draw truth tables for A plus bar. See if it's the same. And if it is the same, then this proves the point of this equal sign. With that practice, I think it may be difficult to give you a picture of why it will be useful to start practicing the truth tables. Even if you know the solutions, you know that these are equal. You know, I know these are equal, but I understand the importance of practicing on the truth tables. Because with that practice, in the future, it will be much easier to manipulate these numbers, even without knowing the laws. You will be able to manipulate the numbers. All these laws allow to reduce sizes of circuits. I've already made that point. As we've seen, the behavior of the digital circuits can be represented by truth tables, also waveforms and symbols. We have dealt with truth tables. We will deal with the waveforms later. Symbols. Our symbols, these are our symbols. And these are our symbols. Or let me share my screen, photos. We have other symbols. All right. My photos are going to get. What is on the screen?
Yeah, we've got there's commutative law, associative law, distributive law, absorption law.
I don't want to show this one. Just a minute. Let me share my screen. I want to show symbols and other gates, type of gates we use. Okay, share the screen. Voila. These are some of the gates which we use. Will this pen work? No, doesn't work. Why does it work? Okay, these are some of the gates which we will be using. All right, we have the AND gate. It's visible, right? gates, the ends, and is the screen visible?
Yes.
Right, so we have the AND gate. This is the operator and the symbol, the function, the truth table. You have the operator, the symbol, the function, and the truth table. So we have the AND, we've discussed this one. The OR, we say this one is the same as A times B. Okay, in this case, X times Y. Or this is X plus Y. You can show X plus Y using the truth table. 0 plus 0, 0, etc., etc. Right. We have the inverter. When you have X, the other side you have X bar. This is another way of representing X bar, which is X naught. When you have 0, output 1, 1, output 0. Inverter is also known as, this is the NOT gate, inverter or NOT gate. NOT operator, NOT gate, NOT function. Right, we have the buffer. We probably won't be using this one. We have the NAND. NAND, it is AND bar. NAND, it is AND bar. The opposite of this one. This X is the opposite of this one. If I have a 0 here, it means I have a 1 here. Not a 0, a 1 here. A 0, a 1 here. A 1, a 0 here. Then we have NOR, which is OR with a NOT. So this Y is the opposite of this Y. The symbols, you need to know these symbols, because you're either given a circuit with only symbols like this, and you're asked what is the output. A, B, you have two inputs. You're given a circuit like this. In symbols, you are asked what is the output. You need to know what this symbol represents, what this symbol represents, what is its truth table, what is the output. How do you find the output? You find it from the truth table. Once you understand what is the truth table, then you can combine all the outputs you have here to give only one output. For example, here, I know I have two inputs, A, B. If I have two inputs, I have 4 variables. If I have two inputs, I have 4, not variables, 4 possible combinations, 0, 1, 0, 1, 0, 0, 1, 1. I have A, B at this point. Let's call this point Z. At point Z, here we have an OR gate. So it means a plus, 0, 1, 1, 1. At point X, we have two inputs, A and B. Here we have an AND gate. It means at point X is input A and B, the product of them. 0, 0, we have 0 here, 0, 0, 1. We have point XY. Point Y. Point Y, it has inputs Z and X. So these are the inputs at point Y. What is the logic gate at point Y? AND. So what is X and Z? Multiplication. 0 times 0, 0, 1, nope, 0, 0, 1. What is Y? Y is equals to F. This is my output. You are given a circuit like this, and you are asked, find the output. This is your output here, 0, 0, 0, 1. You can be given a circuit in its function form. You can give a circuit in its function form, like this. You need to understand all the representation. It may be given like this: AB plus DC plus D. Find the output. What is the output? You are given a function like this. What is the output? What do? You go and construct your truth table. What does the truth table have? It has A, B, C, D. That's how many inputs? 4 inputs. How many outputs should it have? 2 to the power of n, which is 2 to the power of 4, which is 16 outputs. You construct your truth table with A, B, C, D, 0, 1, 0, 1, 0, 1, 0, 1, until you reach 16 outputs. Now, from the knowledge you have of the operators, of the symbols, of the truth table, and of the laws, it means you are ready to get into logic design. You are ready to go into combinational circuits, what we call combinational circuits. You are ready to go into sequential circuits. But before we get there, you need to understand this first. So let's continue with Boolean algebra. Let's continue with Boolean algebra. Questions, comments. I think I've said a lot of things here. Anything you don't understand, anything you didn't get, anything you feel is too complicated, this is your time to say something. I've introduced variables, ones and zeros. I've introduced functions A, B plus C. I've introduced laws, example, De Morgan. I've introduced gates, logic gates, and or NAND. I've also introduced what else? What else have I introduced? I think that's it. Truth tables. From your function, you can find a truth table. How many variables do you have? If I have n, not variables, inputs. If I have n inputs, it means I'll have 2 to the power n outputs. Now, with this, let's move on to questions. Questions, comments. So far, what we've covered variables, functions, laws, gates, truth table. By now, you should be able to construct your own truth table. If not, this is your time to comment. Oh.
Hello, sir.
Yes.
Very good afternoon.
Afternoon.
We are most concerned about this, the designing of certain circuits which perform certain functions. So we haven't really touched that, is it?
Okay, the design part. I'll say this. This is my first time teaching logic design, lecturing on logic design. So the thing is, I don't have like a blueprint for you to understand how we are doing things. Most of the times, I go from the design part before I actually teach you on how to design. I'm already designing. For example, here I was already designing a circuit before I already told you how to design it. Because it's all in there. I don't have a formula yet how to give it out to you. But this is what I understand. You will design a lot of circuits. I already have a lot of circuits in my head that I can design, but you are not there yet. I need you to understand the basics first. So it might be a mistake that I already introduced you to the design part. Now you are asking for more, but you cannot get more if you don't understand the basics first. So if you need more of designing now, it won't be the case because you don't understand the basics yet. So understand the variables, the functions, the laws, the gates, the truth tables. After that, we will get into the design part. We have my adders, we have full adders, half adders, which we'll be designing. We have circuits which do conversion. I already talk of conversion. How do you convert a BCD number to a gray number? There are circuits which do that. How do you design those circuits? We will get to that part. But what we need to understand now is how do we get there? How do we get there is by understanding what a variable is, what a function is, what is a gate, what is a truth table. And from that, we get to the designing part. I feel I've said a lot, but did you understand where I'm going, Masoka?
Yes, you have answered me, sir. I'm understanding. Thanks very much, sir.
Right. Any books you would recommend us to go through? Right. The thing is, concerning my references, the thing is, I don't have any. Most of the things I lecture here come from the notes I got from my professor, my lecturer, when I was doing the same things. Now I'm only supplementing, I use Google. If you use Google, if you use YouTube the way it is supposed to be used, you will get this information. For example, I don't even know what a variable is. I just go on Google and say variable PDF. I open 10 tabs of variable PDFs. I go through all of them. I get a number of definitions. I pick which definitions are okay for you to understand. Those are my sources. So for everyone who's going to ask me, what are your sources? I don't even know. The internet is my source. The internet is my source. I don't have books, references. And I don't think right now is the time for using those books. I believe those books are supposed to be used when you are doing research. When you are doing research, when you are part force, when you want to do citations, you want to do a formal thing. I got this from A, B, C, D. That's where you need proper references. For now, you need information. You need to understand. How do you understand? Go on the internet, find sign bit magnitude, and you will see that 0 is not the same as Mr. Madondo gave you. That's how you learn. This is my process. I think other lecturers, they will give you references and all that other stuff. But for me, everything is your reference. Everything on the internet is your reference. And with that, we have 10 minutes left, and I don't think I can start on anything else with that 10 minutes. So I'll leave the session for any other comments and questions. Any other comments and questions? Unmute yourselves, please. Discussion. Let's discuss logic design and switching circuits. Let's discuss that. Do you get where we are going? Let's discuss it. Unmute yourselves. Participate as a Omashiriri. Say something. Even a good afternoon say. That is participation. Participate. Do you understand where we are going? Yes.
Yeah, I understand.
Ina murongo ne request you mentioned.
Yes.
Ndeyekuti atikwanisire kumweta lesson iri kuma tangana 2 every day.
Nope.
11 yenenge kuti let's say mwatete mabasa.
All right, I cannot because I have a timetable. For this one, I only made an exception because I had something else to do at 11. But the timetable sticks. I think today's lecture is at 11. Mondays is at 11 again. So if you are at work, you have to stick with the videos. Unfortunately.
Yeah, I think 11 is actually the best. Yeah.
Yeah, there comes another one. 11 is actually the best. Oh, 11,
it's okay.
11
okay.
double. But I understand when we're going to and I'm always open for any questions. Data, I can actually do it on the weekends for you only if you don't understand what is going on. Unfortunately, the system we are using now, it doesn't have part-times and normal students. We used to have conventional students Mondays to Friday, part-time students on weekends, but now we don't. So if you feel like is those guys you are going to work, you don't understand, you are not catching up, buy me data, comrades. Or you can come to the campus, you buy me lunch. We'll probably go through the whole course on those weekends. Advice. If not, you stick to the recordings. Comments, questions?
Set it a plan, you say.
Right. My questions. Unmute yourselves, everybody, please. Unmute yourselves. Unmute yourselves.
Yes, sir. I can see the direction.
Where?
The lesson was well explained.
Thank you very much. Now, what I need my distinctions. Mukangogumira kuti tikuona chiri kuitika ka musingandipe promotion my distinctions, it doesn't work. I need my distinctions. You won't get them all the easy, obviously, but I do need them. So if you're understanding the direction I'm gonna say, I need distinctions as well from you. All right.
We will
We'll try our level best, eh?
Where
definitely give them to.
voila, that's the spirit. Because I've already said this to the students I taught last time. This is my second year. Students I taught last time. This is a win-win situation for us all. I don't want you to fail. Because if you fail, it means I'm also failing my job. You understand? I do not want you to fail. So if you fail, it really means you don't know anything. You are that dumb. If you fail, you don't know anything. Because I actually don't want you to fail. There are instances where you have lecturers who have a reputation for failing students. You actually go into a lecture knowing that you are going to fail. This is not the case for me. For me, if you fail, no disrespect. It actually means you are dumb. You are dumb. No disrespect. All right. So at the end of the year, please remember, no disrespect if you fail. All right. Any other questions and comments? Questions and comments, ladies and gentlemen. Let's go. Portia. Question. Comment.
Azafaya.
Zulfa. All right. Computer engineering. Computer engineering department. I had a discussion with what was his name? Brandon. And I was asking him if he could relate to what we are doing to what computer engineering is. I think he mentioned he is doing computer engineering. He actually could relate. Any other instances of people who are at computer engineering department who at this point do not relate to what they are doing with this course? Maybe to understand, why are you doing this course? Why are you doing it? For telecommunication guys, I don't even need to tell you why. For network engineering, same, physical layer. For computer engineering, guys, I don't even know. But that one is an A. When I saw one computer engineering department, why are you doing logic design? One body for computer engineering.
Yeah, very poor materials, very poor.
Murugu zero, Murugu is logic design.
Rumbidza ingatauri.
Rumbidza zvanzi Okay. I will assume they know what they are
We
doing.
are still trying to figure it out.
Which program do you do?
I do computer engineering.
Yeah, Bunda Brandon. And Brandon,
Brandon.
Munokazirama IC circuits, right?
Yeah.
Do you know what IC circuits are made of?
Not yet.
Okay, you will see.
Rumbiga.
You will see. Okay, I think we are done with this session. Thank you very much for participating.
Mr. Madondo.
Yes, comrade.
Will you allow me, since you are now closing, maybe it's out of context. I wanted to know, are you taking people for internet programming?
Nope.
Okay,
I'm only taking, this year I'm only taking logic design, routing and switching, signal processing. Only those three.
Okay.
Okay.
Thank you, sir.
Right. I think we are done for today. Have a good weekend. Ciao.
Okay.
Thank you.